All right, so we're going to be talking about strain gauge. And the first concept, of course, is what is strain, right? And strain is a proportional change in length. So it's not simply a length, like is it 1 meter to 2 meters or 1 millimeter to 2 millimeters, right? But it is a percent change, right? Like it's a 10% increase. And that is a relevant quantity, as you're aware, in a lot of applications, right? Where you don't want to know necessarily how much something expanded, right? But how much it expand relative to its size, right? Because that will determine things like when it breaks and so on, right? And this is an idea you sort of know. So that is strain, right? And now the question is, how would you measure it if you had to? I want us to think again about a resistor as an object, right? And we did this already. And I said that when you have a resistor that's an object, its resistance in ohms is equal to its resistivity, let's call that in ohms centimeters, times the length, let's say in centimeters, over the area, right, in centimeters squared, right? So here's your, same color. Here's your length. Here's your area. And the thing that it's made of is the resistivity. So this is the basis for how we think of a physical resistor. And I said that when a resistor is a sensor, so when a resistor is, let's say, a sensor, then its resistance is a function of the measurand, the thing you want to measure. And the only way that's possible is if somehow, right, the measurand, let's see if I'm lucky with these, if somehow the measurand is affecting one of these quantities. For example, right, if temperature affects the resistivity, then your resistor is sensitive to temperature, right? If we have some way, as we talked about with potentiometers, of changing the length, then we have another position sensor, right? A strain gauge is also a resistive sensor. And the best way to understand that is I want you to imagine if I took this object here and I stretched it a little bit, right? So it's and I pull it out. So what would that look like? It will look, if I were to, well, I'll exaggerate it a little bit, maybe something like this, right? I pull it apart. And I remember in a previous class when I was asking you a question about which of these parameters change, you were giving me answers that related to this intuition, right? So what do we see in this case? We see here that we have a new length, right? And it's obviously longer because I stretched it. But the area here, call it A sub 2, right, is smaller, right? As I pull it out, if you imagine this is a balloon. So let's imagine what that would do to the resistance, right? So this quantity here went up, right, which would make the resistance bigger or smaller? Bigger. But this quantity went down, so that would make the resistance also bigger. So suddenly we can see that if we take an object and we stretch it out, right, it will impact its resistance. Now it turns out that the resistivity could also be impacted by the fact that we're stretching it. As we're stretching something, right, we're changing its material properties, right, we're ripping things apart. So resistivity could also be impacted, right? So we'll put that maybe, here we have like a resistivity 2. And if you understand this, you understand the physical principle for a strain gauge, because that is what a strain gauge is. All right, you understand how a stretch can produce something. The way strain gauges are used is they need to be attached, as in glued, to the object. So in this case, I would take the strain gauge And right here, I would attach it, if you can imagine my picture here, to the, let's say this is a beam now. And it has to be glued in place. As you'll see, it can't just be hanging out. As the beam bends, right, we know that the length of the top will slightly increase, right? But guess what's glued to it? The strain gauge. So the strain gauge goes along for the ride. Does that make sense? In fact, if there is a 10% increase in strain on the beam, there is a 10% increase in length of the thing that's attached to it, right? Notice the strain gauge does not need to be the same size as the beam because we're interested in proportional changes in length. So we're getting exactly what we want. Now, to implement this, we would simply need to measure the resistance from end to end. So I have an end here, and I have an end here. And that resistance is a function of strain, right? Now, what is the exact equation for that, right? Because whenever we're giving a sensor, whether it's a temperature sensor or anything else, I have to give you an equation with it. It's not useful without it, right? So we need to think about that a little bit. And one way to try to get some intuition about that is to consider this equation in terms of proportional changes in resistance. And I'll show you what that means. I will rewrite it here to say that I'm interested in a change in resistance over an initial resistance, and that is going to be equal to any change in resistivity over an initial resistivity plus any change in length over an initial length minus any change in area over an initial area. Now you can get to here from here by differentiating, but just think about this intuitively. If resistivity, just resistivity were to double, well, so would the resistance, right? If just length were to go up by a factor of 1.5, so would the resistance. It would also go up by a factor of 1.5. And if area were to go up by a factor of 2, then the resistance would go down by a factor of 2, right? And moreover, it turns out that the change in area and the change in length are not independent. You may have heard there's something called Poisson's ratio, and it turns out that when this thing happens, right, there is a relationship, right, between the length and the area. They're not independent. If I know that the length went up a certain amount, as long as the volume is the same, then I know the area must have shrunk as much. So these actually are not independent, and so what people will do is they'll write, therefore I'm going to get a change in resistivity over resistivity plus a change in length over L, and this will be 1 plus 2 times a number. This number is Poisson's ratio. But this is just a number, okay? So what I've done here, the only reason what I've done here is I've gotten rid of this delta A over A to just give me my delta L over L, all right? And now I'm going to do one more step, and I think at this point things will start to feel a little bit more motivated. Now I'm going to write that the delta R over R per, and I'm going to divide by delta L over L, is equal to delta resistivity over delta L over L. Hopefully my notation here is clear. Plus, in this term here, 1 plus 2 theta. Okay, what has been, this in fact to me looks more complicated than that, so what has been achieved? And why is this considered the most useful equation for a strain gauge, right? Because think about generally what we want when we develop a sensor. Let's think about temperature, right? I want, let's say it's a temperature resistive sensor. So this would be R of T, right? And in the simplest world, right, the simplest equation I might come up with is something like alpha times T, right? So whatever the temperature is, the resistance is some multiple times that, right? We know it's not ever going to be this simple, but you get the idea that this, when I'm looking for an equation for my sensor, I need something where I get resistance on this side, right? And the measurand on that side, and then there's going to be some sort of quantities here. Now, I wanted strain, right, which is why I went to this proportional length. And now it's telling me something. It's telling me that the change in resistance is going to be related to the change in length by this factor. So this factor here is called the gauge, with an A, gauge factor. Let's use a big G to celebrate that. And what you see here is we now just have a single constant, right? There's a single constant, right? So I can say that the change in resistance over an initial resistance is going to equal the gauge factor times the strain. And this is a number. G is just a number. So I appreciate that going from here, we kind of backpedaled into some complexity, but look where we emerged on the other end. We have something that looks exactly like this, right? And to just write it out, we can say that for a strain resistive sensor, we have the delta R over R is equal to this gauge factor times delta L over L. And this constant here, right, is given. This is given. When you are buying a temperature sensor, you're given a temperature coefficient of resistivity or something else that's relevant for it, right, like a beta. Guess what? When you go to Amazon and you're buying a strain gauge, it just comes with a number, right? And some may have a number 3 and some may have a number 20. And that's all there is to it. Now, I need to say at this point, the chance that any of you are going to work with strain gauges is extremely low, right? Send me an email if in 25 years you are the CEO of Strain Gauge Incorporated, and you're like, you wouldn't believe it. So when I go through examples like this, and there's 1,000 I could pick from, the point is not to make you masters of strain gauges. The point is to show you that across all biomedical instrumentation, it's the exact same things over and over again. And so you can see that as long as you understand that resistors are physical objects with these parameters, and anything that changes these parameters will change the resistance, including a stretch, right? So that's a physical principle. From a physical principle, we can go to a rather simple equation, right? You're not going to make a strain gauge, you're going to buy one, right? And now we're left with the next step, which is to put it in a circuit, right? You can't look at a strain gauge and be like, oh, I know what your resistance is, right? You have to take, so if this beam is bending and this resistance is, and so this strain gauge is stretching and its resistance is changing, how do you know that? So you need to put it in a circuit. And what circuit is that? What circuit would you use? Let's say voltage divider. Maybe someone else was going to say Wheatstone bridge, so we'll go there. So you're right. Let's start with voltage divider. Let's do that first. Put it here. And you go like this. You would take a battery, E. You would take an R fixed. And then right here is our, let's call it the R strain for strain gauge. You would measure the voltage, V out, from here to here. Boy, does that look familiar, right? And we don't, now you see, and you're ready where you already know what this is going to do, right? We can now write it out just to remind ourselves that therefore V out is equal to E times R sub S over R sub S plus R fixed, right? And what's the equation for R sub S? Well, R sub S is equal to G times delta L over L. You have all the information you need, right? If I were to give you, now we want to be a little bit careful here because we're now very interested in how the voltage is changing, right? It is very important at this point, right? But if the voltage started at 1 volt and it became 2 volts, you would be able to calculate how much this resistance changed. And by calculating how much this resistance changed, you would then be able to figure out how much the strain changed. We're not introducing any new concepts here. And as we go through the course, you will see this again and again. If I gave you a resistor whose resistance changed with pressure, you would have a pressure sensor. If I gave you a resistor whose resistance changed with blood glucose concentration, you know how to make a blood glucose concentration. All right. Yes?
So previously we derived it was the change in resistance with respect to the initial resistance. Why can't we say that over here?
Oh, I'm sorry. You're right. I'm wrong. I'm wrong. Thank you for correcting that, okay? Thank you for correcting that. But again, this is not such complicated math, right? You could calculate things out. I now want to go back, and we're almost done, okay? We're almost done with this. I just want to go back and bring back the Wheatstone bridge and show you something very interesting that you could do with the Wheatstone bridge. So instead of this circuit, the only other circuit, right? Well, I shouldn't say that. We have circuits with op amps, right? But the main circuit we have for coupling our sensor so far, right, is the Wheatstone bridge. So let's redraw that. Here we have our source E. We're going to have an R1, R2, R3, R4, and we measure the voltage out between these 2 points. And if we were to call this V1 and this V2, right, then we have V out is equal to V1 minus V2. And again, I'm going through this quickly because we've done this before. And therefore, E times, the remember here, it's going to be R sub 2 over R sub 2 plus R sub 1 minus R sub 4 over R sub 4 plus R sub 3. This is the equation. This is V out, right? This is the equation right here for a Wheatstone bridge, as opposed to, right, the equation for a voltage divider. All right. Now we have a sensor here that is sensitive to this beam bending, and we could theoretically put it into this circuit. right? And the question is, where would you put it? And the short answer is, it actually doesn't matter. For example, I could put it right here. So I'll put that as this. So this means that this is now the strain gauge. Why? So as the beam bends, this resistance value will change, which will change V1, which will therefore change the output. However, doing this is no better than the voltage divider. And we've gone through this as to why, as far as sort of sensitivity, right, we don't get much of a change. But we did go through what would happen if you added another sensor. So now I want to go back to this example here. Or I'm going to redraw the beam here in a bigger, a nice clean beam to work with. And we glue on one strain gauge, and we will glue on another strain gauge. And each one of these has its terminals, of course, because it's a resistor. And now what I'm going to do is I'm going to call this my, I'll call this my R sub 2. And I will call this my R sub 3. So now this is also a sensor here. And as we're building it, we better keep our terminals straight, right? These two terminals are from here to here. And these two terminals, right, are from here to here. If you created this versus this, all right, you would find out that you have a more sensitive device. In a hypothetical situation where, let's say, your neighbor built this and the beam bent and they saw a 2 millivolt change, right? In your circuit, you would see a 4 millivolt change. Now, both of your circuits work, right? Now, the way you could have messed this up is if you had taken this and instead put it here, right? It really matters that it's on the opposite side, right? And let me review why that is. So let's say this resistance goes up, so it's getting bigger. That means it takes more of the voltage, right? So therefore, this voltage is going up. In this case, as this resistance goes up, it takes more of the voltage, but that means this one gets less. So this voltage goes down. So as this side is going up, this side is going down, and that's what gives us the most bang for the buck. If you put this here, your circuit would be completely non-functional. And we've gone through that example, right? I know we went a whole, right? So just refer, if it's not clear, but if this goes here, I mean, think about it, you now have a mirror image, right? What's on this side and what's on this side is the same, so V1 will always equal V2. So you cannot put this here because V1 and V2 will always be the same, and so you're just going to measure 0, 0, 0. Is that clear? Yeah? Now here's something else you might do wrong. You might say, you know what I'm going to do? It's kind of crowded on this side of the beam. So what I'm going to do is I'm going to glue it to the bottom side of the beam. And again, we have two terminals here. Right? You're thinking, well, I'm just going to go to the bottom. I mean, a beam's a beam, right? Why would this be of concern? Any idea why this might not be a good idea? Putting some on the top and some on the bottom? Yeah, go ahead, because? Right, it's compressing. As I've shown you here, if this beam bends, right, this length will go up, but this length will go down. So it's the opposite. Yeah.
So then, should the orientation of the sensor also be along like the length of it as
Correct, and we want to be careful about where we're measuring. Right, exactly. It's a great point as well, right? This way would not make good sense. I agree. And so this one is interesting. So if we would notice that if the beam, we'll go back to this example, if the beam is in fact bending this way, then this resistance here is increasing, right, by up. This resistance here is increasing, but this resistance here is in fact decreasing. So if instead of R3 here, I put R3 here, things would again not work out very well. What would happen is, let's say R2 is on the bottom, right? R2 starts to get bigger, so this voltage gets up. But R3 becomes smaller, so this voltage goes up. So if you glued it not here, but here, you'd be at a deficit, all right? Now we're ready for the 4-arm Wheatstone bridge. When people say arms, what do they mean? Well, there's always 4 arms on a Wheatstone bridge, right? Did you think I wrote something else, Adrian? What did Oh, like a yarm? Yeah. 4-arm, okay. Let's do a 4-arm. I'm going to add yet another one here. I'm sorry, running out of ink. I'm going to keep the same color if I can. I'm going to add another one with its own wires. I'm going to make this one R1. I'm going to make this one R4. And I want you to notice that R4 is also decreasing. So now, in this situation here, all of them are sensors. But I want you to notice that some, let's call these ST for sensors on the top, and these are going to be SD for sensors on the downside. I guess I could have bottom. All right. They're not the same, are they? And now let's think about what would happen. As the beam starts to bend, these ones up here stretch, and their resistance goes up. These ones down here compress, so their resistance goes down. When you do this, you're going to get an output that is 4 times more sensitive, approximately, than this circuit. So if this circuit would have changed, your next door neighbor made a circuit and it changed 1 millivolt, your circuit would change by 4 millivolts because there's 4 things working for you. This one is going up, making the voltage bigger. This one is going down, making the voltage bigger. This one is going up, making the voltage bigger. And this one is going down, making the voltage bigger, right? And I can send you a link where this is sort of derived, right, with some approximations. But what I really want you to get is I want you to get the intuition, right? That you understand how each one of these resistors is affecting the output, and you understand why a 4-arm works. But a 4-arm only works when you have 2 going up and 2 going down. I could have asked you, well, if I put all 4 on the top, what would have happened, right? And hopefully, if you thought about it for a second, you would say, well, that would be bad again. Because if all 4 are on the top, well, then they're always the same, right? If 1 is 1, the rest are 1, right? So 1, 1, 1, 1, right, means that this voltage is the same as that voltage, means the output is 0. Now the beam bends. 2, 2, 2, 2. Nothing has changed. Output is 0. Beam bends some more, right? 10, 10, 10, 10. So putting them all on the top also doesn't work, right? Now, you'll have some hands-on experience you'll get some with a 4-arm Wheatstone bridge. I think you sort of understand how it works, all right? Now, notice we're measuring the voltage from this point to this point, right? And you could do that with your multimeter, right? Do you happen to know any other circuit that is really good at taking the difference of the voltage between 2 points that we learned about? A circuit that measures and then gives you the difference between the voltage of 2 points? One of the circuits we covered when we talked about operational amplifiers. Which one is it? Is that? Right. There's in fact a difference amplifier whose only job is to measure the difference. And in fact, there's something even better than that, right, which is very equivalent, which is the instrumentation amplifier. So in fact, you could slam on an instrumentation amplifier here, and it would do this difference for you. But we'll get there. But I'm trying to show you how everything's connected. So far, so good? All right. Will you ever see a 4-arm like Wheatstone bridge outside of this class? I highly doubt it. All right? But there are some lessons to be learned here, and I'm going to give you one more lesson. And these lessons, by the way, the lessons apply to every biomedical instrument, right? So that's where we're really focusing on the lessons.